Morning and welcome to Symbolic Logic Unit 10. Today we're going to be learning about formal rules for conditional and biconditional. These will add to the previous formal rules that we've already looked at for conjunction and disjunction. And eventually, next week, we'll be learning rules for negation. And this will bring us through to have all of the formal rules that we're going to have for our system of natural deduction. Okay, so let's turn to some examples of formal rules for these two connectives used in ordinary language or ordinary reasoning. So first of all, consider this policy. This is a policy that's in place at Lawrence about honors exams. So here's the policy. Only the student participating in an honor exam and an examining committee consisting of only faculty members are allowed into an honors exam. Thus, everyone in an exam room during an honors exam is either a student or a faculty member. Suppose we can see into an exam room, but we can only see Sheldon. As ignorant observers, we know that Sheldon is either a student or a faculty member. But which is he? Based only on appearance, perhaps we don't know. Still, it follows that if Sheldon is not a student, then he is a faculty member. So consider this idea. Sheldon is a faculty member or Sheldon is a student. From this reasoning, we can infer that if Sheldon isn't a student, then he is a faculty member. Here is a formal representation of the reasoning here. We know that Sheldon, again, F represents Sheldon is a faculty member, S represents Sheldon is a student. So we know F or S. And now we can infer that if it wasn't the case that S, then it would have to be the case that F. We still don't know if Sheldon is a faculty member, but we know this thing is true, that if he is not a student, then he is a faculty member. So what sort of formal rule might ground the introduction of the sentence containing the conditional here? And again, that sentence is, if it's not the case that S, then F. Well, look, what we're doing here is we're reasoning to a conditional statement. So this is an example of reasoning to the conditional. So the rule that we would use here is conditional introduction. So again, let's walk through the reasoning. Notice that if we knew that Sheldon were not a student, we could use our disjunction elimination rule to infer that he is a faculty member as follows. So we could say either he is a faculty member or a student, and if we know he's not a student, then we can use disjunction elimination to infer that Sheldon is a faculty member. And all we need to cite again, just to remind you of how this rule operates, is the disjunctive statement, F or S, and the negation of one of those disjuncts. So not S at step 2, or premise 2. So that's given to us. So notice that this reasoning is perfectly plausible. We introduced it last time. So it seems to follow that if this were the case, then if it's not the case that S, it follows that F. Right? So if we can make this move, if we can infer from not S to F when we're presented with F or S, then it seems to be a valid inference or a valid sentence in its own right to say if it's not the case that S, then it is the case that F. So conditional introduction provides a rule to show what would be the case if some supposition were to hold. Right? Again, it allows us to show that if something were the case, then some other thing would happen. So it provides us a way then to demonstrate the truth of a conditional, a way to demonstrate that if something were the case, then something else would follow. Okay, so let's look at this rule in formal representation, as it would be formally represented. So here's the way that it works. So again, at step one, we might have some sentence. Let's say F or S again, to stick with our example. So this is our given premise. Again, we know that everyone in the room is either a student or a faculty member. Now, what we're going to do to show that a conditional holds is we're going to make a supposition. And so this is our first time using suppositions in our derivation system. But notice what we've done here is we've added a little Fitch bar underneath the other Fitch bar. And so what that shows is that if this is an embedded Fitch bar, right, in other words, it's not the main Fitch line, then whatever occurs above the bar is an assumption, okay? Things that occur above the bar on the main connective are premises. But if they occur above the bar on an embedded Fitch bar, then they are assumptions. They're things we're supposing to be true, but we don't know to be true. Premises we know to be true. These things we're just supposing to be true for purposes of an argument. And I'll show you how we use this assumption to demonstrate something else. Right? So in effect, what we're doing in introducing this assumption is we're saying, what could we show if it's not the case that S were true? So what would follow from the assumption that not S, or what would follow from not S? So again, it's important to note that we don't know Sheldon isn't a student, but what we're doing is we're supposing that this were the case to see what follows. And so clearly it follows from this assumption, from it's not being the case that S, that F. And the way we would get to F is very simply through the application of our disjunction elimination rule from our premise 1 and our assumption at 2. Right? So we've shown if not S were true, then F would follow. So if we've shown that, then we've just shown from our assumption that if Sheldon isn't a student, then he is a faculty member. Right? So notice we didn't pull it's not the case that S out of this subproof and state it at the main level of proof where the things that we know to be true are stated, nor do we pull out F that Sheldon is a faculty member from inside of that subproof. But what we did was we used some reasoning to say, okay, suppose this thing is the case, then this other thing would follow. And so what we cite here is, we actually cite this whole subproof that ran from assuming that it's not the case that S to F. And what that subproof shows is, not that not S is true or not that F is true, but that if not S were true, then F would follow. Okay, so that is what we've demonstrated using our assumption that not S. But it's important that we never pull any of these sentences that occur in the subproof out to the main level of proof, because we're just doing suppositional reasoning here, reasoning about what might be the case if some other things held, and we're not actually demonstrating that any of these things are true. Okay, so again, our conditional introduction rule establishes a conditional by showing what would be true if something else were true. So we just showed if this thing were true, then this other thing would be true, and that is a conditional. Okay, so why is this useful? Why might it be useful to show that if something is true, then something else would follow? Well, in fact, there are lots of instances in which this kind of reasoning might be useful. Right? So if I want to convince you of something, Z, and I know you're already committed to Y, then showing you that Z follows from Y would be very useful. Right? So maybe for a politically charged example, I want to convince you that abortion is wrong. And so I know you're committed to murder being wrong. And so now I show you that if abortion is murder, then it is wrong. Right? So that's a kind of argument that people give in the political sphere. And it relies upon this assumption. If Y, then Z. All right, so let's look now at the details of this reasoning, at the conditional introduction reasoning. So we're going to see how we would represent this rule in a formal way. right? Well, notice, again, we justify our application of conditional I by citing the entire subproof, right? So that's why we use a dash. Notice when we cited disjunction elimination here, we pointed to these two premises. What we said in effect was that if premise 1 was true and assumption 2 was true, then this other thing would follow from that. But when we use conditional introduction, we're showing something through an entire subproof, not just the use of individual premises. So what we want to cite is that entire subproof. And this is a very short subproof. It just has one assumption and one step. But oftentimes these will be longer. They may run as long as 10 or 12 lines. So you would cite all of that just with the dash. And it may at first seem that you can get something for nothing using conditional introduction, right? So for example, you can do the following. We can reason from nothing, from no premise, and then assume that A is true, reiterate A beneath that as one step. That's clearly a valid move. If A were true, then A would follow. And then we can assert that if A is true, then A follows via conditional introduction. And we do that through steps 2 through 3. But we didn't rely upon any premise whatsoever to do this. So it seems like we've shown that some truth holds from no ideas whatsoever. Well, in fact, this is as it should be, because if A, then A is a tautology. It's a logical truth. So we shouldn't need any premises to demonstrate it. There's no situation in which it can be false. So it doesn't matter what is true in the world we're considering for us to be able to demonstrate that if A is true, then A is true. So this is as it should be. So the conditional introduction rule is very powerful because it can show things that hold even though we don't know anything else is true. But those things will always take a conditional form when it demonstrates them. Okay, so the general form of the rule is as follows. So again, remember we use M and N to stand for unknown numbers. So these are variables for premise or step numbers. So how we use this rule is that at M, we assume our sentence that is the antecedent of the conditional that we want to demonstrate. So we assume phi here. And remember, phi is just standing in for any sentence letter whatsoever. And I find it helpful to make a note here, the author of your book does too, to tell yourself where this subproof is going to end. So you know actually where you've, you know when you've ended up where you need to end up, and you know what you need to shoot for. So again, we assumed phi at step M. This is just an assumption. And then what we showed was that it follows from phi's being true and whatever else is known, that psi is true. So we've derived at what we wanted here at line N, psi. And so now we're in a position to jump out of the subproof and to assert at the main level of proof that if phi, then psi. And that is, again, conditional introduction, and we would cite all M through N. Okay. So within the subproof, we can reason from anything that occurs outside of the subproof above it at either a higher level of proof. You know, at some point later on, we'll see subproofs embedded within subproofs. And 2 levels in, you can refer to things in the governing subproof there. Or you can also pull things from the main level of proof that are premises or that have been demonstrated outside of the subproof. But we can't ever refer back once we're outside of and below a subproof. We can't refer back into the subproof to pull any information out from there. Okay, so that's an important step. We'll be seeing this in use a lot coming up. Okay, so another point here is that our example of conditional introduction worked from a disjunction above, right? So the last one we were looking at involving Sheldon, the faculty member of students or student, we relied upon the disjunction elimination rule. But obviously this doesn't always have to be the case. So consider for this, for example. So if we know if B, then C, we can assume A and B, use conditional or use conjunction elimination from 2 to derive B, and then derive C from premise 1, if B, then C. And so we could derive, we've actually demonstrated in this case that if A and B, then A. I think that should actually be if A and B, then C is what we have demonstrated. So that's a typo there. Sorry about that. So we've demonstrated here if A and B, then C via conditional introduction from 2 through 4. But notice this didn't rely on disjunction elimination at all. The important thing, the important pattern to notice in conditional introduction is that we're moving from an assumption to some intended goal. And the thing we assert outside of that subproof should have as the antecedent the assumption we made to start the subproof, and as the consequent, the last premise that we ended up with within that subproof. Of course, this example doesn't have that, and that is because I screwed it up with a typo. This last A here should be a C instead. Okay, now you may notice that there is a premise that appears in here, conditional, that relies upon a rule that you haven't seen yet, and that is conditional elimination. We're going to turn to look at that rule right now. So we've just seen how we can reason to a conditional statement, but we can also reason from conditional statements. This will prove very useful as we do derivations. So consider a very standard argument against abortion. So this is similar to the argument I gave just a minute ago. Premise 1, if a fetus is a person, then it has a right to life. Premise 2, a fetus is a person. Conclusion, a fetus has a right to life. And it follows from that, people will argue, that abortion, the killing of a fetus, violates its right to life and is therefore wrong. So I think this is a standard argument that many of us have heard before. So whether or not this argument is sound, it is certainly valid. And it relies on a premise of reasoning that we're going to introduce right now, or a rule of reasoning that we're going to introduce right now, called conditional elimination, or in fancy Latin terms, modus ponens. So you may have heard this concept before, modus ponens. And this is that style of reasoning. So how does this argument work? Well, clearly here at step 1, we are presented with something of the form, if phi, then psi. And then at step 2, or premise 2, we're presented with something of the form phi. And now we know if a fetus is a person, if it's true that if a fetus is a person, then it has a right to life, and it's true that a fetus is a person, we are able to derive psi from that. And so the rule that we're able to derive that with is the rule we're introducing now, conditional elimination. And in using this rule, we would cite 2 premises. Notice we're not citing a whole subproof here, so we're back to using commas. And we're going to cite a conditional premise and the antecedent of that conditional, and those 2 things allow us to derive the consequent of the conditional, right? So imagine you have a statement, if Thumper is a cat, then he's fuzzy, right? And you know that Thumper is a cat. Well, clearly you can infer from that he's fuzzy. If those 2 things are true, this follows. And we can come up with lots of examples of this reasoning. It's perfectly standard for us to use this inferential move in ordinary reasoning. Okay, so I hope that the conditional elimination rule was clear. I think the conditional introduction rule is a bit more of a heavy lift. Let's practice a proof that uses both of these rules. Right? So we actually saw an argument above that used both conditional introduction and conditional elimination. That's how I introduced the idea of conditional elimination, but here's another one. So suppose we're presented with if P, then Q. And we also know if Q, then R. Well, through these 2 ideas, we may want to demonstrate, because the conditional relationship is transitive, right? We know that if P entails Q and if Q entails R, then P will entail R, right? So we know that this is a valid form of inference, right? And we can think of examples of this. So we can stick with the cat example. So suppose we know if Gary is a cat, then Gary has mammary glands. And if Gary has mammary glands, then cats give live birth, right? So we can infer maybe from that if Gary is a cat, then cats give live birth. A bit of a strange inference there, but you could think of other examples that will motivate this. So the idea is that once we have this part of this antecedent, then we can infer this consequent. And once we have that as the antecedent of this step, we can infer this consequent. So we want to demonstrate that if P, then R. So what we do is we can assume P here. And again, we know that we want to end up with R at the end of this chain of reasoning. That is this subproof. Well, clearly, through a single application of conditional elimination, we can derive Q from step 1, if P then Q, and from step 3, P. And then if we have Q, we can infer from step 2, if Q then R, and step 4, Q, that R follows. And so we'd use, again, another instance of conditional elimination to get that from premise 2 and step 4. And so now we've shown that if P were true, then R would follow. So what we've shown is, in fact, a conditional, and we're in a position to assert that now via conditional introduction. And again, we cite the whole premise, steps 3 through 5. Okay, we're going to turn now to looking at the biconditional. So remember, the biconditional, in effect, says if and only if. So it's asserting if you have A, if and only if B, that the conditional arrow or the conditional horseshoe goes both directions between these two antecedents and conditionals. In other words, each of these, each thing on either side of the biconditional symbol is an antecedent to the other thing on the other side of the biconditional, and that thing is a consequent. So what we want to show is that the conditional arrow runs both ways. And so here's an example to help illustrate this. Suppose we want to argue that something can feel pain if and only if it is a human brain. So that's the only way that something can feel pain, right? If something feels pain, then it's a human brain. And if it's human brain, then it feels pain. Okay, so if we wanted to demonstrate that this biconditional is true, what we would need to show is that each of the conditionals that make it up are true. So we would need to show, first of all, that if something is a human brain, then it is capable of feeling pain. And maybe that's not too difficult. We know we have a lot of experience with people have human brains, and it seems like that's importantly connected to their capacity to feel pain. But having shown that, we haven't shown everything we need to show. We need to also show that the conditional arrow goes the other direction. So we also need to demonstrate that if something feels pain, then it is a human brain. In other words, that feeling pain necessitates human brainedness, right? And that would be a much more difficult thing to demonstrate. There seem to be counterexamples out there. Speaking of cats earlier, they seem capable of feeling pain, but they lack human brains unless we redefine human brain in some unusual way. So this is a general pattern of reasoning behind a conditional introduction, biconditional introduction. And so what we do is we essentially perform two conditional introductions. We show at some point that if phi is true, then psi follows, and we show at some other point that if psi is true, then phi follows. So these two steps, M and N, need to appear at some point in your argument. There will obviously, if you're deriving these conditionals, you'll need subproofs to derive those conditional statements. They could also be given to you, so you could have a simple argument that just starts with M and N as premises and asks you to demonstrate the final conclusion here, phi if and only if psi. But in some way, you have to cite those two things. Okay, so that's the general pattern of reasoning behind biconditional introduction. What about reasoning from a biconditional? Well, this one's actually great, and it's very powerful. So if we think about our conditional elimination, it said, well, if you had, if we had a conditional statement, if A, then B, it said, you can, if you have A, then you can infer B from that conditional statement. But we can't go the other way. We can't infer A from B, right? So consider example, if Gary is a cat, then Gary is a mammal. We can infer, from knowing that Gary is a cat, we can infer that Gary is a mammal. But if we just know that Gary is a mammal, we can't infer that he's a cat. He might be a monkey or something, right? This one says, if Gary is a cat, Gary is a cat if and only if he's a mammal, right? So in this case, it goes both directions. And the rule functions like this. We can infer if we know this thing is satisfies a condition on one side of that biconditional, then the other one has to hold. So another example here is built on an odd fact. There's a genus of mammal called Podus flavus, and it contains only one still living species, and that is the kinkajou. So the kinkajou has its own unique, I think it's order actually, of mammals that it belongs to. So there's the guy, he's pretty cute. Well then, it follows that if we know that this is a kinkajou, then we know it's a member of Podus flavus. And if we know this is a living member of Podus flavus, then we know it's a kinkajou. So we can assert a biconditional between something's being a member of genus Podus flavus and something's being a kinkajou, and we can draw the inferences either way. So to generalize, the rule, the biconditional elimination rule looks like this. It's basically a generalized version of modus ponens. So if we have at step M, if phi, or phi if and only if psi, and we have at step N, phi, then we can infer psi using biconditional elimination from M and N. Alternatively, if we have at M, psi if and only if phi, or phi if and only if psi, then we can infer psi from that thing. And if we have psi, then we can infer phi from that thing. So basically what it's saying is you can go either direction so long as you have the thing that counts as the antecedent for the other thing using biconditional elimination. And again, here you're going to cite two premises. You're going to cite the biconditional and then the thing that is serving as the antecedent in your reasoning, in your application of the biconditional elimination rule. Okay, so that's it for this section. I'm going to link to a Moodle video in which I demonstrate several derivations using the rules that we've now established. Let's give you a little bit more visual introduction to these rules, and then I'll be giving you some exercises to practice on as well. Okay, I will see you tomorrow during our class meetings. Goodbye.